Hello, everyone. Today I am going to present our work titled Adaptive Controller VR Enhanced Fine Motor Assistance through Finger Pressure Modulation. Virtual reality interaction faces a fundamental challenge. On the one hand, users need to perform large finger movements in 3D space. On the other hand, they must also accomplish millimeter-level precise manipulation. In practice, this means users constantly need to switch between coarse and fine operational granularity. However, most current interaction techniques do not explicitly support this transition in a natural and seamless way. That at the same time, human motor control offers an interesting insight. When we grasp an object, muscle co-contraction regulates our grip. Increasing grip force generally improves control precision, but excessive force may introduce tremor. Inspired by this mechanism, we asked whether finger pressure during controller use could reveal a user's intention for higher precision. If so, we could use this signal to provide adaptive assistance, allowing users to interact more naturally and effortlessly across different precision levels. To explore this idea, we developed a low-cost hardware solution using thin-film pressure sensors attached to the controller. These sensors capture the pressure applied by each finger during interaction. In this work, we primarily focused on index finger pressure, as it plays a central role in common VR manipulation tasks. Our research centers on remote interaction with 2D interfaces in VR, and we investigate two main questions. First, does finger pressure outperform conventional control metrics, such as object displacement or trigger values, in identifying or predicting operational precision? Second, if it does, how can we model and apply this relationship effectively in practical VR applications? To answer the first question, we conducted a user study using a drag-and-drop precision task. The experiment followed a 4x4 within subject design, with 4 movement directions and 4 endpoint widths, repeated 8 times per condition. 16 participants took part, and we collected 2,048 valid trials. As expected, smaller endpoint widths made the task more difficult and required finer control. During the task, we recorded finger pressure, object velocity, and trigger values. When examining the data, we observed that trigger value typically rose quickly, reached maximum value early on, and remained unchanged, and object velocity sometimes showed multiple peaks and more variability. In contrast, finger pressure tends to stabilize after an initial rise. Correlation analyses revealed that both the mean and peak finger pressure, as well as mean object velocity, could distinguish different levels of precision demand. However, the peak of finger pressure demonstrated the largest effect size while being minimally influenced by movement direction. This finding could also answer our first questions. Moreover, unlike lagging indicators such as average pressure, the peak pressure can be estimated early in the interaction. This makes it particularly suitable for predicting user precision intent in real time. Based on these findings, we constructed a simple pressure precision model using our collected data. We compared several common fitting functions and found that a sigmoid function performed best. The sigmoid curve captures threshold and saturation effects that align well with human perceptual and motor behavior. It also allows smooth transitions between different precision levels that to evaluate the practical effectiveness of our approach. we implemented it in a slider-based target-finding task. In this task, shorter target segments require more precise control. We designed an adaptive method that dynamically adjusted the control display ratio near the target region. This helped users perform fine adjustments while naturally slowing movement when higher precision was needed. We compared three conditions: a baseline without insistence, a fixed high-precision control display ratio, and our adaptive method driven by predictive precision from finger pressure. The figure provides the ideal ratio for the adaptive method, but the actual ratio is affected by the user's index finger pressure data. 12 new participants joined this study. The results showed that the adaptive method improved both speed and accuracy in difficult tasks, while preserving fast performance in easier ones. Participants also rated the adaptive condition more favorably. To further explore generalizability, we apply our approach to a VR drawing scenario. In detailed drawing, users typically zoom in to improve stroke control. Instead of full-view zooming, we introduced a brush-following magnifier with adjustable zoom levels. One condition used manual zoom control via the other controller's joystick, while the adaptive condition adjusted zoom implicitly based on index finger pressure. 8 participants completed calibration tasks, practice sketches, and 2 formal tracing tasks. The calibration tasks include coarse-grained single-line drawing and fine-grained single-line drawing, while the practice sketch and formal tracing tasks need to be completed using 2 control methods. As mentioned, objective drawing quality was comparable between methods, with a slight advantage for the adaptive approach. Subjectively, participants reported lower mental demand and effort when using adaptive control, even though usability ratings were not significantly different. Overall, our findings show that finger pressure is a continuous, natural input modality with strong potential for enhancing precision interaction in VR. A simple continuous model can support lightweight personalization and adapt to different classification granularities. Importantly, this pressure-based method does not aim to replace existing interaction techniques, but rather to complement them by transforming certain explicit controls into implicit ones, thereby reducing workload while maintaining performance. There are limitations to our work. The sample size was relatively small, and the resulting model may not generalize to broader populations. Our experiments were limited to 2D interfaces to reduce directional and rotational uncertainty. The method also requires brief user familiarization, and individual variability was not fully explored. But in the future, we plan to validate our approach with larger and more diverse participant groups, extend it to full 3D interaction scenarios, integrate movement trajectories for multimodal robustness, and explore whether pressure can predict interaction modes, such as anticipating whether a user intends to click or grab when approaching an object. In conclusion, we explored the potential of finger pressure as a channel for inferring user intent and providing adaptive assistance in VR. Our results suggest that fingertip pressure can serve as a powerful implicit signal to support fine motor control and improve interaction quality. Thank you for your attention.